Have you ever looked at a beautifully crafted stone wall, sturdy and strong, holding back maybe an entire hillside, and wondered how it stands there?
Hmm.
Or maybe, on the flip side, you've seen those walls that, well, they sag or crack or just look tired after only a few years.
Yeah, you see that sometimes.
It often comes down to one crucial, kind of invisible detail.
Huh,
It's geometry.
that's it.
Today, we're diving deep into a really fascinating aspect of retaining wall design that honestly, most people probably never consider. Why curves aren't just pretty. Why they're often the unsung heroes of stability and longevity.
That's absolutely right. We're going to unpack why a gently sweeping curve can, well, frankly, outperform a sharp angular corner pretty much every single time when it comes to segmental retaining walls or SRWs.
Right, those dry, stacked block systems you see everywhere.
Exactly. And we're talking about the fundamental engineering principles here, what makes a curved wall inherently superior, and also some of the very specific construction techniques that we at DIY Retaining Wall use.
DIY.
Based on industry-leading guidelines from places like NCMA and, of course, our own extensive field experience to make sure these curved sections are, well, not just beautiful, but incredibly robust.
So our mission today is really to uncover those critical differences, curves versus corners in SRW design in construction, and focusing particularly on how the strategic use of crushed stone and precise compaction techniques, how they're absolutely vital.
Crucial.
Yeah, vital to making those curves hold up against those huge earth pressures.
Mm-hmm.
And this isn't just theory, right? It's
Okay.
practical knowledge, stuff that will change how you see retaining walls forever, whether you're planning a big project, maybe a small garden bed, or you just want to understand the kind of hidden engineering marvels all around us.
Absolutely. It applies across the board.
Okay, so let's start with the absolute basics,
Right.
because this is where the magic or sometimes the misery really begins. What is the fundamental difference in how these earth forces behave in a curve versus a sharp corner? Why does geometry matter so much?
Well, it's really all about how that force gets distributed. Imagine, pushing on something. If you push on a flat surface, the force is concentrated right where your hand is.
Okay.
Now think about pushing on something curved, like the dome of a helmet or even an eggshell. That force gets spread out, doesn't it? Dissipated across the whole surface.
Ah, right.
And that's essentially the inherent advantage of a curve, especially what we call a convex curve, one that bows outward, away from the soil it's holding back.
Okay, outwards.
Yeah. It naturally distributes those immense soil pressures much more evenly across its entire face. Think of it like an arch. An arch is incredibly strong precisely because it channels and distributes compressive forces outwards and downwards.
So it's kind of like comparing an egg to a shoebox. An egg's surprisingly hard to crush if you apply pressure evenly all around.
Right.
But a shoebox, with those distinct corners, it just collapses much more readily if you press on the sides.
Exactly. That's a great analogy. Those sharp corners on the shoebox, they're weak points. And in a retaining wall, sharp corners act like stress concentrators. Stress concentrators.
Yeah, the lateral earth pressures that sideways push from the soil that's always there, they basically converge on those corners. It creates these areas of incredibly high stress. It's like trying to hold back a rushing river with just a single pointed stick instead of maybe a broad curved paddle. That stick is going to snap.
Right. It makes sense. And since these SRW systems, they're dry stacked, you mentioned, they rely on friction and gravity, and they're actually designed to allow for some minor subtle movements without cracking.
Correct. That flexibility is key.
So those concentrated stress points at corners become really problematic then, don't they, because of that inherent flexibility?
They absolutely do.
Yeah.
While that flexibility is generally a huge benefit for SRWs. I mean, it's what stops them from cracking like a rigid concrete wall might.
Right.
It also means that any area with high stress concentration, like a sharp corner, is far more prone to issues. You'll see things like blocks starting to gap apart, maybe developing hairline cracks, or even just slight bowing right at those corner sections over time, even if the rest of the wall looks okay.
Yeah, exactly. Even if the rest looks perfect. Curves, on the other hand, by smoothly distributing that load across the entire arc, they just manage this inherent movement much, much better.
Okay.
It leads to superior stability and a wall that really performs as a single cohesive unit. The very abrupt change in direction at a corner just creates these isolated zones of intense pressure. That can lead to long-term instability.
Okay, so if these earth forces are the sort of invisible enemy and curves are our natural ally in distributing that force, what's the secret weapon? What do we use to really supercharge that curve's performance, especially when dealing with those subtle but mighty pressures. I'm guessing it has something to do with the strategic use of crushed stone or gravel fill.
You've absolutely hit on one of the most critical elements, and it's one that's often overlooked by folks who maybe don't understand the engineering behind it.
Right.
Crushed stone isn't just, backfill you dump in. It's a meticulously engineered component, especially when you're designing for curves and corners.
Meticulously engineered.
Okay, this material is absolutely key to managing that soil pressure, ensuring you can get proper compaction back there, and directly preventing those aesthetic and structural issues, like the cracking and gapping we just talked about.
Ah,
It really is a secret weapon. It absorbs and distributes pressure in a way plain soil just can't.
so it's not just any gravel, and it's definitely not just about throwing it in there carelessly. The depth of that gravel fill matters profoundly, you're saying.
Yeah.
Especially in those curved sections and, I guess, corners, too?
Oh, definitely.
What are the specific guidelines we follow at DIY retaining wall, based on those NCMA standards you mentioned?
Right, well, the wall rock design guidelines are actually quite precise. For walls that curve inward, what we call inside curved or inside cornered walls.
Okay, curving towards the hill.
Yeah, where the curve sort of hugs the retained soil. For those, we can generally use the minimum specified wall rock depth. And here's where it gets really interesting for those outward curving walls or outside cornered walls.
The ones pushing against the soil.
Exactly, the ones really bearing the brunt of the pressure. We strongly recommend an additional depth of wall rock there.
Why is that?
Well, because this greater mass of free-draining, highly compactable material directly behind the SRW unit provides extra protection. It's fighting against that increased soil pressure generated by the wall's geometry itself.
Oh.
And it's particularly vital if there's any chance of, say, traffic load at the top, even just foot traffic, or a heavy lawnmower regularly going over it.
Right, that extra weight pushes down and out.
Precisely. That additional weight, called a surcharge, adds to the lateral pressure the wall needs to withstand, so that extra gravel gives it more backbone.
And what I find really remarkable is that your guidance, it isn't just a sort of blanket recommendation like use more gravel. It's tied directly to the wall's dimensions, the geometry. You have specific radius-based guidance for these gravel widths. That's really the engineering shining through, isn't it?
It has to be specific. It's all about making those invisible forces, well, tangible through design. Let's try and make those numbers a bit more real for people listening.
Yeah, good idea.
Okay, imagine you're building a wall that's, say, 6 feet tall. That's H, the height.
Okay, 6 feet.
Now, if you're planning a very gentle sweeping curve, maybe one with a radius R of 12 feet, so R is twice the height, 2H.
All right, a wide curve.
Yeah. For that, our guidelines suggest you'd need about an 18-inch layer of crushed stone right behind the blocks. That's H divided by 4, or a quarter of the wall's height.
18 inches wide, okay.
But what if you want a tighter, maybe more dramatic curve? Perhaps a radius of only 6 feet. So R is equal to H. R is 1H.
Same as the height.
Okay. Then the recommendation jumps significantly. It goes to H divided by 2. So for our 6-foot wall, that's suddenly a 3-foot deep gravel bed behind the blocks.
Wow, 3 feet. That's substantial.
It is. And if you're trying to create a really tight curve, maybe almost semicircular, say with a radius of just 3 feet, now R is 0.5 H, only half the wall's height.
Okay, really tight.
Then you're looking at a full H gravel width. So for that 6-foot wall, you'd need a 6-foot deep gravel bed behind it.
A 6-foot deep gravel bed for a 6-foot high wall.
That's right. Though typically not deeper than the Geogrid reinforcement length, but yeah, potentially that much.
Right.
It really demonstrates how crucial these specific ratios are. You're compensating for the immense forces generated by those tighter curves, giving the wall the inherent strength it needs right there in the fill material.
Wow, that really puts the numbers into perspective. A 6-foot deep gravel bed. That's some serious engineering foresight right there. It's not just guessing.
Definitely not guessing.
But what about those sharp corners we talked about? Not the smooth curves, but actual angles. Do they need that same kind of strategic gravel treatment?
Absolutely. The core principles still apply, but the specifics, they shift slightly based on the angle.
Okay.
So for angles between straight wall segments, say, where your wall turns a corner if it's a gentle turn, from 150 degrees down to maybe 115 degrees.
Like an obtuse angle.
Exactly. You'd need that H4 gravel width, similar to the gentle curve. But for tighter turns, say, from 115 degrees down to a sharp 75 degrees.
More like a right angle or even sharper?
Yeah. Then the recommendation increases again to H2 gravel width.
Half the height again?
Right. Again, it's providing that vital greater mass of protection right where that pressure concentrates at the corner. By making sure you have this thicker gravel fill area directly behind the block, especially in the vicinity of those tight outside radii or sharp corners, that's really the most effective precaution against the blocks cracking and gapping.
So it prevents those ugly gaps.
Exactly. And look, even if some minor movements aren't necessarily signs of catastrophic failure, they are definitely an aesthetic concern, and you can significantly mitigate that with the right gravel design from the start.
Okay, so the right kind and the right amount of gravel are critical. But I imagine that gravel isn't going to do its job properly, no matter how perfectly engineered the depth is, if it's not put in correctly. Which brings us to compaction, the often unsung hero, as you said, of wall performance, and probably especially crucial for those complex curved sections.
Whoa, you absolutely cannot overstate the importance of compaction. I mean, consistent compaction is mandatory for SRW structures to perform as a composite unit.
Composite unit.
Yeah, think of the wall blocks, the geogrid reinforcement, the soil behind it, and that crucial gravel fill. They all need to work together as one giant, strong, interconnected block.
Okay.
If one part is spongy or loose, the whole system is compromised. And in our experience at DIY Retaining Wall, improper compaction is honestly one of the most common issues we see in installations out in the field.
Really, what causes that typically?
Often it's due to excessive lift thicknesses. People try to save time by dumping too much material, soil, or gravel in at once before compacting.
Trying to do too much in one layer.
Exactly.
Yeah.
And it simply doesn't get dense enough throughout that thick layer. The compactor just rides over the top.
And for curves, where we've established the forces are so meticulously distributed, precision compaction in a very specific critical zone is absolutely vital, right? What unique construction techniques do we recommend for that?
Right. So for the first 3 feet, that's about 914 millimeters directly behind the wall face, this is what we call our critical zone, especially important for curved sections.
The first 3 feet.
In this zone, we specify the use of hand-operated equipment only. Ideally, this means a vibrating plate compactor.
Like those walk-behind ones.
Yeah, walk-behind vibrating plate compactor with a minimum weight of around 250 pounds or 113 kilograms.
Okay, why that specific type and weight, not heavier?
Well, the why here is really important. Using lighter weight, sort of lower energy equipment right in this critical zone minimizes the potential for settlement directly behind the SRW units themselves.
So you don't want to shake the blocks too much?
Exactly. If that area settles too much after the wall is built, it can actually overstress the connection between the geogrid. Remember that strong mesh-like fabric we lay back into the soil for reinforcement?
Yeah, the grid.
It can overstress the connection between that geogrid and the wall unit itself. And that connection is absolutely vital for the wall's overall stability. So we don't want to jeopardize it with heavy, jarring compaction equipment right next to the blocks.
So it's not about brute force then. It's more about a kind of nuanced, almost gentle persuasion for those gravel or soil particles to lock tightly into place.
That's a perfect way to put it. Precision, not brute force.
Are there any common mistakes maybe DIYers or less experienced installers make here?
Yeah.
Perhaps using the wrong type of compactor or just rushing the process?
Oh yeah, several common mistakes. One is using compactors that are too heavy, too close to the wall face. That can actually cause the blocks to shift or tilt out of alignment, which is a nightmare to fix. Another is using equipment that's too light, maybe just a hand tamper for the whole job, which simply doesn't achieve the necessary density, especially in the gravel zone.
Right.
And then there's the lift thickness issue we mentioned. Trying to do too much at once. Lift thickness should never exceed 6 to 8 inches, about 200 millimeters.
6 to 8 inches max per layer.
Max. And sometimes, especially if your soil conditions aren't ideal, you might even need to reduce that further, maybe down to 4 or 6 inches, to achieve the specified compaction densities. You have to test it. And here's another crucial technique, especially for curves, that many people miss. You must compact parallel to the face of the wall.
Parallel. Following the curve.
Exactly. Following the curve with your compactor, making your first pass closest to the wall face, and then working your way back, layer by layer.
Okay, not just going straight back and forth perpendicular to it.
Definitely not. If you compact straight across or just sort of haphazardly, you inevitably end up with non-uniform compaction. And that leads directly to vertical and horizontal alignment control problems down the line.
Which would be really obvious on a curve.
Oh, incredibly obvious. Believe me, in a curved wall, any misalignment is not just structurally problematic, but it's also highly visible. It completely takes away from that beautiful, sweeping aesthetic you were trying to achieve.
Okay, that makes a lot of sense. So beyond the critical gravel and the meticulous compaction, what about other considerations? Like geogrid placement, especially when you're dealing with the added complexity of corner stability.
Yeah, geogrid reinforcement is, of course, essential for pretty much any reinforced SRW wall over a certain height. And convex corners, those outside corners, they introduce some very specific, sometimes tricky considerations for laying that grid.
How so?
Well, imagine you have two layers of geogrid that, because of the corner geometry, end up needing to be placed at the same SRW unit elevation right at that corner. They'd essentially try to occupy the exact same space.
Overlapping right on top of each other.
Right. You can't just lay one directly on top of the other. For proper anchorage, the guidelines state you need a minimum of 3 inches, that's about 76 millimeters, of compacted soil fill between those overlapping reinforcement layers.
3 inches of soil in between them. That sounds tricky to get right.
It can be. Which is why, as a smarter alternative, especially what we recommend at DIY retaining wall, is often to place the geogrid in the perpendicular principal direction on the succeeding course in that crossover area.
Okay, perpendicular on the next course up. What does that mean in plain English?
Yeah. Sorry, bit technical there. Basically, instead of having 2 layers compete for the exact same horizontal spot on one layer of blocks,
Right.
you can stagger them vertically. One layer goes out from the corner on one course of blocks, then on the next course of blocks going up, you place the other layer running perpendicular to the first one.
Okay. Like you're weaving a basket almost at the corner.
That's a great way to visualize it. It provides that strength in both directions, but avoids the tricky overlap issue. But it really highlights how much more complex the design thinking and the actual construction become at corners compared to the smooth, continuous flow of a simple curve.
Yeah, corners seem to require a lot more meticulous planning and execution.
They generally do, yes.
And finally, I guess, after all this meticulous design, the gravel depths, the compaction plan, the geogrid layout, a consistent visual and structural check throughout the actual building process is paramount, isn't it? Because even the most brilliant engineering on paper needs vigilant oversight in the field.
Oh, absolutely. We preach this constantly at DIY retaining wall. Continuously checking for the alignment of the wall as you build is simply non-negotiable.
Checking constantly.
Constantly, every course. It's vital for both the wall's aesthetic appeal, making sure that smooth, flowing curve looks absolutely perfect, and arguably more importantly, its long-term structural integrity. You're always sighting down your lines, checking your curves against your layout stakes, making sure everything is true and plumb, level front to back. This continuous verification is what takes a wall from simply, standing up to truly standing strong and beautiful for decades to come.
So, okay, let's try and bring this all together. Building a curved retaining wall might, at first glance, seem maybe more challenging than just a straight one, or one with simple corners, because of that added geometric complexity.
It can seem that way initially.
But, as we've really unpacked today, understanding these core engineering principles, things like the natural force distribution that a curve offers, the really strategic and precise use of crushed stone to manage pressure behind it, and those meticulous compaction techniques required for optimal performance. Understanding all that actually makes the curve not just a beautiful design choice, but an inherently superior, more durable, and ultimately a more reliable structural option.
That's exactly our fundamental belief, and it's what we put into practice every single day at DIY Retaining Wall. We're really here to help folks, navigate these complexities, ensuring you build safer, more reliable structures that are going to stand the test of time. And it's all based on robust engineering guidelines, like those from NCMA, coupled with decades of our own direct field experience. It really is about building smarter, not just harder.
Build smarter, not harder. I like that. So here's a final thought. Next time you see one of those beautifully curved retaining walls, maybe along a highway or in someone's yard, don't just admire its aesthetic appeal, its graceful lines. Take a second and consider that invisible dance of forces happening behind it. Think about the strategic layers of crushed stone, the careful compaction, and the meticulous engineering that allows it to stand so strong, gracefully defying the immense pressures of the earth pushing against it.
It's quite amazing when you think about it that way.
It really is. And maybe ask yourself, what other invisible engineering solutions might be hidden in plain sight all around us, making our world safer, more stable, and more enduring, maybe simply by understanding and harnessing the geometry around us. We really encourage you, the listener, to start looking for these fascinating details in the world around you and maybe consider how this knowledge might empower your own future projects.